Okay, well, so my name is Doug Durian. I'm from University of Pennsylvania, and I'd like to thank the organizers for giving me this opportunity to tell you about some experiments we've been doing. Here, I'll focus on dynamical heterogeneities in 3 different systems, not just on their existence, but in particular on how they grow as we get closer and closer to jamming. The first system is from the PhD work of Adam Abate, and it's a monolayer of basically ball bearings. It's about a foot across. We blow air in here. The balls are on a porous plate. And we blow air not hard enough to levitate the balls, but to excite uniform motion through turbulence in the gas. In the second system, which is part of the postdoctoral work of Hiroki Katsuragi, we're going to pour sand at a pretty high rate at the back of a narrow box. Let it build a pile and flow down. And we'll do it at a high enough rate that there are no avalanches. Rather, the flow is uniform and continuous. It's nice and smooth and fast near the top. As you go down deeper, the speed gets slower and slower. So there's a jamming transition as a function of depth. The last system is part of the PhD work of Kirsten Nordstrom, and this is in collaboration with Emily Verneuil, Paulo Ratia, and Jerry Golub, where we're going to pump a soft colloidal sphere system, NIPA particles, through a microchannel. And in this system, jamming is going to be approached by 2 ways: by throwing in more balls and also by turning down the gas speed. In this system, jamming is approached as a function of depth. So here the control parameter is really density, and something I'll show you is like effective temperature. Whereas here the control parameter, well, experimentally it's depth, but really it turns out, I'll show you, it's going to be shear rate. Here the control parameter is also shear rate. But also density. We're going to control the density of the colloids. And we're interested, as I said, in seeing how the dynamical heterogeneities grow as you approach jamming. So why jamming? Well, it's because that's where we don't have a good handle on things. Far from jamming, at high temperatures, low densities, very high driving, we understand things, right? You've got ideal gases, you've got, under high loads, you've got granular theories of hydrodynamics, or just based on expressions of continuity of mass, momentum, energy. We know how things work. But as you turn down the temperature, as you increase the density, as you turn down the load, the tools that we know and love and that we use and we teach our graduate students start not to work or fail in unusual and interesting ways, and basically we get into trouble. So all the interest is in what happens as you go towards jamming, and unusual and interesting things happen that you don't expect. That's why I like to go there as an experimentalist, because we find things that we didn't have intuition for. We see unusual behaviors that we didn't expect. And one example of that is that even though you may be driving the system at a steady clip and a steady rate, pumping in energy in a very even-handed way, the system doesn't respond uniformly. There's something unsteady about the response. And that unsteadiness actually grows as you get closer and closer to jamming. Just by way of a little more background, that turns out to be a sort of an overarching theme for a lot of things that are going on in my laboratory these days. The classic example, of course, is avalanches. Say you have a bucket of sand and you tilt it. If you tip it fast, if you drive it hard, it pours out like water. Right? It's nice and smooth and continuous. But if you tip it slowly, it goes intermittently by avalanches. So you're driving at a steady rate, but you get an unsteady, intermittent response. Happens in foams. I spent a long time working on the way rearrangements of bubbles from one tight packing configuration to another are driven by coarsening. And, for example, how the rate of rearrangements and the shear rate interplay with one another. If you shear fast or slow compared to the strain rate, you see different behaviors. Of course, there are lots of examples of this in the natural world. In the laboratory, we also look at impact. So drop a ball into a bucket of sand. When the ball hits the bucket of sand at first, it's moving in, you're driving it very hard. Continuum theories work very well. But as the ball starts to come to rest, you start to notice that unusual things happen. For example, force chains are coming and going. They're being formed and broken intermittently, and that causes unusual dynamics for the impact. If you poke a hole in a bucket of sand at the bottom or in the side, and the hole is large enough, the sand will flow out in a nice, smooth, uniform way. It will just keep going until the bucket is empty. But if the hole is small enough, it'll flow for a while, and then suddenly and unpredictably it'll clog. And there's some distribution of flow times and discharge masses and so forth, depend on the hole size and say the tipping angle, the nature of the materials and things like that, which we're very interested in. So steady driving, unsteady responses. Elsewhere, well, outside my laboratory in particular, I usually don't work with vibrating sand, but periodically driving sand, putting on a shake table is something that's very popular to do because there's just a whole wealth of behaviors that crop up. You can get phase separation and coexistence between sort of liquid-like and crystalline regions. You can have very slow compaction and density changes, convection, size segregation. Lots of interesting, unusual things can happen if you inject energy periodically, but at a steady rate. Maybe even more simply is just let some sand, at least in a computer experiment, cool. So you have an inelastic gas where you dissipate a little bit of energy every time there's a collision. Just set it up with some random speeds and let it go, and it'll slowly rattle away its energy by collisions. But it doesn't look like the cooling of an ordinary gas. If you turn down the temperature on an ideal gas, of course nothing changes with the density or the anything, right? But if you cool an elastic gas, what happens is you'll develop clusters. You'll get dense regions and rarefied regions. There'll be lots of collisions in the dense regions. You'll develop interesting structures and so forth. And for John, so if you drive if you have active systems, say you have particles or rod-like particles that have some source of energy and they can scoot along, you get unusual behaviors. So it's being driven in a very even-handed way, but you get unusual collective behaviors like swarming and density fluctuations and so forth. And we've been trying to make contact with some of the stuff John has been doing by fluidizing rods. So there's sort of the overview, and of course dynamical heterogeneities. That to me is yet another example of an inhomogeneous response to steady driving. So let's go. Here's Adam, and here's his experiment. This actually is raw video data. So they're ball bearings, about a 1 foot across sample. We work with anywhere from, say, 300 to maybe 1,500 balls. They're shiny. So if you illuminate them from above, you see a teeny tiny white spot at the very center. If you look, I'm not sure if you can see in this room, but if you look closely, you can see a darker spot, which represents the whole ball. So this is a pretty dense sample. Nonetheless, since the illumination is as it is, it's very easy to track the particles. And here's an example. They'll diffuse around through the sample. So as this thing goes, you'll get an idea that the system really does look sort of ergodic. The particle is exploring all of phase space in a very even-handed way. It looks kind of thermal, and I'll actually flesh that out in a little bit.
Excuse me, can you tell a little bit more on the experimental setup and how does the air hit the...
So literally this is sitting on top of a sieve that you would use to sort sand. So it's a screen. And the size of the weave in the screen is very small compared to the grains. So they don't really feel the sieve. They don't feel the weave in the sieve. They move every which way at random. But the gas can come out of those little holes in the sieve very uniformly. So the flux of gas coming out of the page is very uniform. And the pressure drop that drives the gas flow is dominated by the flow across the sieve. So the flow isn't really perturbed in any real sense by the presence of the particles. Nonetheless, the Reynolds number, well, I should say also that we choose a gas speed such that the particles are not levitated. In fact, they're rolling without slipping on the plane. The Reynolds number based on ball size is about 10 to the 4th. So the picture is that these balls are shedding a turbulent wake. And it's the interaction with the momentum in the gas that's kicking these things around at random in the plane.
So the position of the particles, strictly speaking, is discrete because they are always sitting at the bottom of wells.
No. The mesh is so small that they only...
But it's small, but it's discrete. Yes or no?
It's discrete, but the particles can't...
I understand it's irrelevant, but just
right.
in order that I understand it. Principally, if you would take 100 million snapshots, you would see the grid again.
If you would say that again, I did.
100,000 snapshots of the particles. Then you would see that there are sites that are more probable than...
No, you wouldn't. No. No.
So
I think Walter's right. Strictly speaking, in principle, you'd see a difference, but what you're saying is just it's so small you wouldn't
Well,
be able to
as a practical matter, if we look very closely for those effects, we can see them if we turn down the gas speed.
yes.
Okay, so and then we can see that the balls will sometimes they'll roll along a seam.
Yes, exactly.
Okay, so we're in a regime where that doesn't happen.
Okay.
That's all. So we're pretty sure it's very continuous motion. Yeah. All right, so there's Adam again, and he's going to approach jamming by throwing in some more particles and see what happens. So how does this approach jamming? Like a glass. So here it's this. You get all the phenomenology we in this room know and love. So for example, here's the paracorrelation function between the small and the large balls. So I should have said it's bidispersed to prevent crystallization. So at higher packing fractions, the first peak in the paracorrelation function shoots up. The second peak bifurcates. It gets a double peak in the second peak. So that's a standard thing. If you like to count coordination numbers of the particles, fourfold coordinated grains, the probability of finding a fourfold coordinated grain goes to 0 sort of continuously at the transition. So there's a host of very subtle structural changes that have to do with local ordering. Nothing we can tell in long-range ordering. The dynamics, on the other hand, show dramatic changes. So, for example, we see for very sort of dilute systems, you see a pretty simple crossover from ballistic motion a short time. So here, mean square displacement is growing quadratically with time. So that's, if you like, that's sort of the granular temperature. This is the energy scale for particle scale fluctuations. A crossover from ballistic to diffusive in a pretty simple way. If you turn up the packing fraction, you open up a plateau of subdiffusive behavior, and the size of that subdiffusive behavior grows and grows as you turn up the packing fraction. But eventually it always pops out of the cages, if you like to describe it that way, and you get diffusive motion at long times. So that's pretty usual.
John, there was a talk at the granular, a couple of talks at the granular Garden conference coming from kinetic theory people, where they said that for granular materials, this plateau, even if you see it, is much smaller than what you see in typical liquids. So they have granular materials are inelastically colliding hard disks, have a much lesser tendency to get caged than, but that's not something that's,
well,
so they were saying it's striking.
Right, like with molecular systems, we like to think that the collision time is molecular, 10 to the 14th or something, 10 to the 12th or whatever per second. And you can pop out of cages on the order of seconds or something. You know, there's the vast orders of magnitudes. I can't get that. But look, there's several orders of magnitude here. Okay. So I think the point is you want to have a separation of time scales between the short time ballistic random motion and the long time collective diffusion. I think that's the important thing.
So maybe one way of saying it is that the kinetic theory actually can't get to that.
Well, I don't think that there's in principle a real difference. It's just a question of, if as a practical matter, I can't extend this more than 1,000 seconds, right, in the laboratory scale. But in principle, you could. Okay, I'd like to understand. Yeah. I don't understand. I'd like to hear more about that.
So yeah. And that upper plateau is just the finite size of the box?
Correct. You're seeing exactly the size of the box right there. Good eye. And of course, there are dynamical heterogeneities.
Are the finite size effects already seeable at shorter time? I mean, the plateau is a trivial finite size effect, but if you would be able to look at smaller or much larger boxes, would the crossover between the plateau and the diffusive behavior show up at earlier? I mean, show finite size.
We've explored those sorts of questions by putting inserts and smaller sieves in there, and we can't tell that there's a difference. Yeah, the only way we get into funny problems is if we have rather dilute samples, like only a couple particles. Like if you have 5 particles, the wakes of the particles tend to interact with the boundaries, and they tend to collect near the center. But as long as it has a sort of a finite volume fraction, they spread out uniformly, and then we can't see anything funny. Here's a movie of heterogeneities I like a lot. So Adam put this together, and I think it dramatically illustrates the kinds of things that we all like to talk about with heterogeneities. So what this is literally is he's plotting the particle trajectories. He's laying down the tracks over a finite window of time. So you write on one end and you race at the other end, and you do that across a certain time interval. Now, if you were to do this for a very short time interval, you'd be in the ballistic regime, and the particles would just be going every which way at random. You wouldn't see any correlations. If you would do this over a very large time window, you'd be in the diffusive regime, and again, you'd see no correlation between neighbors. But, as Adam has chosen here, if you pick an intermediate time such that the mean squared displacement is comparable to the particle size, then you see correlations as observed here. These string-like swirls that come and go, and those are the dynamical heterogeneities. They're color-coded according to the end-to-end displacement. So that's really the average velocity across that time interval. So red means the largest displacement across the time interval, the most mobile particles, and blue corresponds to the smallest mean squared, smallest displacement across the time interval. They're the slowest, and the colors of the rainbow go everywhere in between. So there we go.
What are the two timescales that we see something fast and something slow?
I didn't hear the phrase.
Sorry. What are the two timescales that we see? We see something fast and something slow. Should we pay attention to that? What's this precessing?
Well,
It's like precessing motion.
The thing does seem to pulse a bit. I don't know whether that's the time scale.
The constellation effect is very strong in watching movies like this.
Well, just it looks like there's some convection going on that's maybe on the scale of the cell. I think that's what. Sorry, Joe.
If you watch long enough, you'll see the man in the moon.
Yeah.
You really have to do quantitative analysis.
The thing is, the motions themselves that light up are kind of swirl-like.
Yeah.
There's no real global convection, though. If you time average, we've looked at velocity fields. There's nothing that's important.
Is there any kind of correlation function with these displacements you can look at?
So I'm going to show you I'm going to show you how we analyze these. There are possible ways to do it in terms of velocity correlations, and Bubble likes to analyze things in terms of velocity correlations. We've taken a different approach. So I'll show you how we will quantify these things. And what we're interested in is really the size of these heterogeneities. Jim, you said they sort of tends to blink in and out. So
and John tells me that's just by psychology.
Well, here's the thing.
I'm not saying it necessarily is.
No.
I'm saying you'll never be able to decide just by looking at the pictures.
That's right.
But I claim
that
Jim is right. It is blinking in and out. And it's basically number fluctuations. Fluctuation is the number of fast regions in the field of view. And that's what you pick up when you measure these fourth order, these chi-4 quantities. So we heard in the workshop one way to define chi-4. Basically, you compute G4 and then integrate it over all space. There's a simpler way to do it that we adopt in the laboratory. I think maybe Sharon Glotzer is the first to write down. It's basically you look at the variance in the decay of some dynamical order parameter. So you compute some quantity that decays from 1 to 0 as a particle moves a certain size. You average over the whole sample, and then you see how you get different decays at different initial times. So for example, here's the system. Maybe blue represents the slow regions and red represents the fast regions. We have more fast regions here than at this instant in time than we do at this instant in time. So the order parameter will decay faster at this instant of time than it does here. So you have a natural variance in the decay depending on how many fast regions you just happen to have at that instant. And the variance then will depend on the system size. So to get rid of that, the variance will go down with system size. So to get rid of that effect, you calculate the variance and you multiply by the system size. And that is literally chi-4.
So, I'm sorry, what order parameter are you actually measuring?
For this particular data, it's a step function. So if the particle moves a distance, say half its diameter.
In some
whenever a particle moves, say half a diameter, its contribution to the order parameter goes from 1 to 0 as a step function.
Moves that distance over the time tau.
Yes.
The time is the horizontal.
Right, in that delay time. All right, so that's chi4. And with this picture of number fluctuations, you can do a little calculation, just counting statistics to get the size of the order parameters. I mean, the size of the fast regions. So let's say there happen to be n particles in your system, or your field of view. And let's say that on average there are small n particles in each of the fast regions. Then the whole effect, the reason for variance, is because there are number fluctuations in the number of fast regions. Just counting statistics, so m plus or minus the square root of m. Then we'll be simple-minded. We'll say the order parameter can have two values. Q0 in the fast regions because it's closer to 0, and Q1 in the slow regions because it's closer to 1. So with those ingredients, you can just straightforward calculate the average order parameter and its variance and solve for the number of particles in the fast region. So that's n star. N star, the number of fast regions, is proportional to chi4. And you can get it exactly if you divide by a certain combination of the order parameters in the fast and slow regions and its average value. I think in Jean-Philippe's overview, he said that chi4, computed as the integral of G4, is proportional to the volume of the heterogeneities. That's what this is too, right? N star, this is the number of particles, so it's literally the volume of the fast regions, just given in units of particles. So how many particles are in a fast volume?
Doesn't this assume that all the fast regions are decorrelated?
Correct. It does, absolutely. So this fast region is not correlated with this fast region. So you make that assumption.
It assumes that, or you find that?
Well, it assumes that, right? We just the square root of m.
Assumes that.
Yeah.
It also assumes that there's nothing subtle going on, like what happens to some active systems where number fluctuations violate the law of its numbers.
Yeah, it's absolutely right. Yeah, absolutely. So other things could happen.
I'm confused. Doesn't chi4 measure the correlations between fast regions and slow regions? Spatial correlations?
No. Usually the way chi4 works is there's a length scale in its definition. But usually you just fix that length scale and you look at it as a function of time. So let me show you some data. So here are 3 different ways of calculating the order parameter. This is, as I described to John, just something that goes from 1 to 0 as the particle moves, say a particle size. Here's something that's not so arbitrary. Olivier Duchot will like to use, rather than step function, the Gaussian. And he'll argue there's a particular value of the width of the Gaussian you should pick. Okay, so maybe there's some arbitrariness here. Here's another quantity that you can calculate. It's the persistent area. This is a quantity that's familiar to me from working with foams. The persistent area is just the fraction of the sample that remains inside the same Voronoi cell after a given time. So as the particles move around, the Voronoi construction moves around too, and the persistent area slowly decays. You can do the same thing with persistent bonds. And Onuki and Yamamoto work with this quantity in 1998. So there you go, 3 different order parameters, 3 different shape decays. They decay at different sort of time scales. The persistent bond actually is the slowest to decay, as you can imagine. There's two particles, they can remain neighbors moving around the sample, and they wouldn't decay, but their contribution to these other order parameters certainly would. So the persistent bond takes longer to decay. Chi4 shows a peak. So these are all, as I was telling Bobo, these are at fixed length scale. Here by hand, here by sort of construction, there's a fixed length scale that's important. And the data is shown as a function of the delay time. And what you want to do is pick out the peak heights.
Wow. So isn't that a measure of a length scale, though?
Correct. The peak height is a measure of the volume, as I showed you. Yes. Okay, so the data here for blue, the sort of light blue, this is for sorry, you can't read this. It's first as packing fraction. So here's denser and denser systems. The order parameter decays at later and later times, later and later times, later and later times. As the system gets denser, the peak heights move out to later and later times. The peak heights in chi4 are always right in the meaty part of the decay of the order parameters. So there's no surprise that those move out. What's nice is that they go up. And that's a sign of an increase in the heterogeneities as you go closer to jamming. It's the growth of those peaks that shows you that the heterogeneities are growing in size. Note that the that up there. So we've got 3 different order parameters. We've got 3 different decay times. We've got 3 different sets of peak heights. Like the peak height of this one is like 25. The peak height of this one is 2.5. The peak height of this one is about 3. Different orders of magnitude for the decay scales. But if I go through the construction, the analysis that I showed you in the previous slide to relate chi4 to n star based on the values of the order parameters in the fast and slow regions, look at this. You get the same size. So we were very relieved when we did this. We thought, okay, we've measured something, we've analyzed it correctly. We don't have to be so careful about our choice of order parameters. As long as we are careful in our analysis of the data, we can deduce a meaningful size for the number of heterogeneities in the fast regions. Here is plotted versus 1 over phi minus phi c. So far from jamming, we're down here, and the number of grains in the fast region is close to 1. As we go closer to jamming, we go out in this direction, and this goes up, grows up to maybe 60, 70. It's a fair amount of growth. And if you want to describe it as a power law, you would say the exponent is about 3/4.
So n is going like phi minus phi c to the minus.
Minus nu.
Doug, what are the 2 different flavors of symbols?
We do.
Oh, you see that's open and closed.
Yes. I can't remember. I don't know. I can't remember. Because we did so many checks. This could be where we analyze a subsystem. I don't know. I'll look it up and let you know. I'm sorry.
So are you using the same phi c as, I mean, where does phi c come from?
Phi c comes from a couple different things, but the best measure for us is to look at the scale of the granular temperature and see where it goes to 0. And it turns out to be around 84%, but
So
depends on the particular system we look at.
So phi c wasn't the fitting parameter in drawing the line, is that correct?
No.
Question about the previous slide. You were showing there the 3 different order parameters, and there is a qualitative difference. In the middle one, it looks like you have something more similar to 2-step relaxation, and you don't see it in the other ones.
Correct.
Can you comment something on that?
Well, this is sort of what you would expect from the structure factor, right? So sort of e to the minus mean squared displacement. So this particular parameter is more like that. If we were to measure something that were a Gaussian, like Olivier Dauchot likes to look at, rather than having a step function cutoff, we would see an intermediate structure in this as well.
Is there, can man show mathematically that this n star is larger than 1? I mean, within your approach, so that basically one is consistent, that it's always a number of particles larger than 1? Because this is what was bugging about this chi4, that you get 10 to the minus 2, and that.
So I don't know if you could put constraints on the values. You know, what's the spread? I don't know.
Because it would be nice.
Maybe we can think about that in this context. All right. So does this exponent mean anything? I'm not so sure. There are some exponents that have to do with growing length scales as a function of packing fraction that have been measured. Andrea has measured one of them. But it has nothing to do with dynamics. It had to do with like the width of the distribution of packing fractions over which you get jamming in a finite size system. Cynthia Olson and Charles Reichardt with their students postdocs had measured the size of a perturbation in a granular system. If you drag a particle through a dense system, the size of the perturbation tends to grow with a similar exponent. Peter Olson and Steve Teitel have looked at velocity correlations in a simulation model, and they find a similar exponent. So there are some measurements out there, but I don't really know how deep is the connection.
Are these all these other examples also 2D systems?
Andrea, is this for 2D as well as 3D?
Yeah, it actually is the same. We find the same thing in 2D and 3D.
Huh.
These are 2D.
Two are 2D.
These are 2D.
But there's at least one example where you get the same exponent in 3D.
So I was saying to Jean-Louis that the packing fraction isn't the only thing that's changing as we put in more particles. Turns out that the temperature is also going down. Actually, linearly with packing fraction. That's how we get phi c. So the granular temperature isn't constant. More things are changing than just the packing fraction as we go out. And that also isn't true in these other works. So we've been...
In a sense, your system is more like thermal hard spheres. You have thermal agitation. And for hard sphere, the temperature is not relevant. So shouldn't you rather than to these granular systems, wouldn't it be more consistent to compare this with calculations for hard disk at some finite temperature?
I think you're right. So let me show you where we've gone along those lines. So for the first step is to take the notion of an effective temperature seriously or not. And Adam has actually done a great job measuring 5 different granular temperatures. So there's 2 balls, so you can measure their average kinetic energies. So that's the usual granular temperature. You can measure the mobility of a particle and its diffusivity. So there's the Einstein effective temperature. And here's one. He would replace one sphere with a weighted sphere. It's got a little mass on the interior at the bottom. So it rocks about a minimum position. So this is like embedding a harmonically bound particle. So it's a thermometer. We can measure its kinetic energy and its potential energy. So there's 2 more granular temperatures. The cool thing is if you don't just measure the averages, you measure the distributions, you find that they're thermally distributed. So here are the probabilities of finding kinetic and potential energies for these different thermometers, and look at that. Linear log plot. It's or log linear plot, it's a straight line. It's a Boltzmann distribution. And they all agree. The total energy distribution for the harmonic oscillator looks like it ought to. So they're all thermally distributed. And actually the 5 different effective temperatures are in pretty darn good agreement. So we can take the notion of effective temperature seriously.
So how do you measure the mobility in this experiment?
So we tilt the sample. And then we take one ball out and put in another that's more dense. So it feels a force down the plane, and we just measure its average speed down the plane. So Lynn Daniels, as part of his PhD work, has been measuring the pressure in these just by doing sort of a law of atmospheres. So if you tilt the sample, they'll pile up more at the bottom, will be denser up here, and you know the gravitational force along the plane, so you know the mass above that you have to support, so you can measure the pressure. And we're busy trying to measure an equation of state and see if we can sort of scale like the relaxation time by a relevant time scale that would be important in a hard sphere system, sort of pressure over mass. And same thing for so the temperature scaled by the pressure. And this is something that Andrea is doing a lot of work on. So we're trying to make contact with that. So that's where we're trying to go with those particular experiments. And we're not, the word isn't in yet. So stay tuned on that.
You have to worry about crystallization.
No, we haven't seen any crystallization in these experiments because it's bidispersed. So we use the same size ratio as people like in their Leonard Jones simulations.
I appreciate that. How large is the dispersion?
It's 7-to-4 ratio, size ratio.
And there's no segregation.
Nope, there's no macroscopic segregation, though if you look closely, sometimes there's little micro scale domains that you can kind of see, but we haven't done much to characterize those.
You can check that just follows counties.
Yeah.
Isn't the mobility of the large and small spheres very different?
Their diffusivities are also different.
So when you are measuring...
So you get two Einstein temperatures.
Or you would get the same.
But I mean, in principle, there's two. I'm just saying there's two Einstein temperatures.
In principle, there would be.
So that gives you 6 temperatures.
Yeah. We didn't do that experiment. He just used one ball.
But the dynamical heterogeneities, there you measure average over all the particles?
Correct. Average over all the particles.
This is surprising. And they feed each other.
I don't know.
So it's really surprising that all 6 definitions of temperature give you, at least all 5 they've looked at, give you the same temperature.
Yeah, so I think that's a really interesting side question to all this work on driven systems is when can you take effective temperature seriously and when can't you? I don't have a good intuition for that. For us, you can wave your hands and say, well, the time scale for the turbulence is fast compared to the motion within the plane. So we've got a nice separation in time scales that it's going to help you out. For other systems like the bubble model and so forth under shear, you don't have that, but it also works. So I don't know where to go, but I think that's a really interesting and important question.
For vibrated tables, you would think you have that too, but it doesn't work there at all.
For the vibrated tables, I wouldn't.
Odds on vibrated tables.
Yeah, I wouldn't think that. I always think vibration is a funny way to inject energy.
It's funny, but it's fast.
Yeah, but it injects it vertically, primarily, rather than within the plane.
Yeah.
Excuse me. Do you know why there are these dynamical heterogeneity from a structural point of view?
So is there a correlation with any kind of structural? No. Not that I can see. So, gosh, I hid the slide. Don't hide the slide. So, right here are some measures of local structure, like the number of sides in the Voronoi construction, sort of how circular is a Voronoi cell, the local density, and so forth. And then here are pictures of the average velocity vectors, the persistent area, the persistent bond. And going down, time is advancing by half a relaxation time, half of tau star. So they persist on the order of tau star, as you expect. But if you try to correlate the structures you see in the dynamics with anything that's going on locally, you just can't see anything.
But, I know Hajime tried to convince us that you want to look at bond correlation functions and things like this. Did you try to look at this? Does it work?
I'm not sure what that is.
Actually, we did something similar experiment under vertically vibrating. And we used polydispersed, 5 different size particles. And polydispersity was 11%. And we saw some exotic order in 2D. And that is.
Was it at the persistent bond? I thought what you were doing was like the persistent bond.
We didn't do persistent bond analysis, but we calculate bond orientational order.
Okay.
And also four-body density correlation. And it also grows in a parallel way. But maybe in
we haven't looked for that.
Binary, maybe it's more difficult to see the structure.
You can try.
Yeah. We can try. We've got the data. We can try. Thanks. Okay, so going on to the next experiment. So this is Hiroaki, and I was lucky to have him join my lab for a couple of years. He had a fellowship from the Japanese Society for Promotion of Science. He's back in Kyushu now. And one of his experiments was to look at this flow, where he poured sand at a fast rate at the back of a box. And he did this in collaboration, actually, with Adam Abate. So here's a movie of what you see with a fast video camera, so this is slowed down quite a lot, I think by a factor of 30. And just looking through the side, these are clear walls, so we can look at the grains near the boundary. You can't look in the interior because it's opaque. The bulk sample is white. You can't look in the interior, but you can look at the boundary. And if you do the optics right, you can get some structure on the scale of the grains, and you can get the sense that it's flowing fast near the top and slower as you go deeper into the sample. As usual, there's no obvious changes in the structure, but there are dynamic changes in the dynamics as you go deeper into the sample. So here's... No. So there's been a lot of work in the granular physics on rough planes. So you have a rough incline, a solid plane that's roughened, and you pour your grains on that. No. This is a box. It's a square box, and this is static sand down here. So the sand chooses its own angle. You don't set the angle. The sand chooses it.
It's a 3D system. It has much more depth than what you're seeing.
It's sort of to scale. The depth is about 1 centimeter across, and it's about 30 by 30 centimeters like this.
So it's very deep compared to the size of what?
Yes, it is.
About 30.
It's about 100 particles across, I think. All right, so here's the velocity profile as measured near the boundary. The average velocity. Hiroki was a hero. Look at this. He's got like 6 orders of magnitude of velocity just thanks to a fast video camera and taking data at different frame rates. So very fast, getting to the surface, and very slow, down deep. The data you can kind of fit to a double exponential if you want, but the point is it just gets slower. There is something funny with the dynamics, and even in this plot. We can also use multiple light scattering to find the fluctuation speed. So I don't want to get into that, but it's something that in my lab we like to do a lot. We take advantage of the fact that sand is white, let photons diffuse around in the sample, and you can deduce information about the dynamics of particles in the interior of opaque samples. And the thing that comes flying out at you is the fluctuation speed for the flows. So the idea is this is the average velocity in the flow direction, and this is the fluctuation around that velocity. Notice that near the surface, the fluctuations are not so big compared to the average. So they're kind of just going down. They're not colliding so much. But as you go down deeper in the sample, the fluctuation speed actually becomes greater than the flow speed. So there's many more collisions. Okay? And then finally it just jams up all together. So there's some funniness in the dynamics there.
By fluctuation speed, you mean the RMS?
Just the variance.
The variance around the average. Here are data on the dynamical heterogeneities. So if you remember the pictures I showed you before in the movie, there's structure on the scale of the particles. So actually, you can measure a dynamical order parameter just using image processing. You take a strip along the flow direction. So it's at a given depth. So each of these colors represents a different depth, and a different strip along that image. And you just cross-correlate that image with the image you get a short time later and see are they correlated or not. And look at the variance in that correlation. It's exactly the same thing. So if you normalize it to decay from 1 to 0, here's the data. So near the surface, it decays very quickly, has nearly an exponential shape. As you go deeper into the sample, it decays more and more slowly, and it has a more of a stretched exponential shape, e⁻² at a time, a little bit broader. At the same time, as we go out, the peaks follow it. Peaks also go out in time, and they get larger and larger. So there's growth of dynamical heterogeneities, not as a function of sample. It's the same sample. We're just going deeper we're just going deeper, deeper, deeper from the free surface.
So what about phi, the packing fraction? I missed that.
The packing fraction, as far as we can tell, is close to random close packing.
So but it doesn't get denser.
But we don't actually measure it. We're not able to measure the packing fraction just by looking at the boundaries. If you measure the structure factor for surface images along strips, I don't know if I have that in here. you don't see anything. Near the top layer, there's something a little bit different. But then deep down, there's not much you can see. Same thing with the height of the peak, first peak in the paracorrelation function. So as far as we can tell, there's a little bit of surface structure. It's a little bit rarefied near the top free surface as grains can saltate and dilate a little bit. But if you go down a couple layers in thickness, probably the packing fraction's constant. Probably.
So it's just being controlled by the shear influences.
Yep.
Do you have any scaling of the fluctuations with the shear rate? I mean, like just how they go with each other?
So, make sure I understand. So you'd like me to plot this as a function of strain rate?
Yeah.
I think I can tell you that, but not on the top of my head. Based on the things that I have here, we can construct it. Okay, so there's the peak heights, and here's what they do. So the time gets longer and longer. It just tracks the strain rate, 1 over the strain rate. And the peak height translates to number of grains. Starts around 1. Look at this. It's a little bit less than 1 near the surface. And it gets larger and larger as you go to the interior. Maybe it's exponential with some systematic wiggles. Or maybe it's not exponential, but it certainly grows as you go deeper down. Okay? So growing heterogeneities. In the lab, of course, depth is the control parameter we use to approach jamming, but that's not what the system does. Really, as Bulbul was saying, it's the shear rate, I think, that controls this transition. This is a strain rate dependent transition. So let's look for the control parameters. The relevant dimensionless parameters would be the temperature scale. So here's the size of fluctuations, fluctuation energy, normalized by the pressure, which for us is just rho g times the depth. It's growing linear with depth because we're pretty close to the surface. And the so-called inertia number, which is a ratio of sort of a grain scale speed with a sort of a sound speed. All right, so here's the inertia number. Here's the temperature. Look at that. They track one another. And the inertia number is about 100 times bigger. So really, I think the strain rate, the inertia number is what's controlling this transition. The temperature scale probably is set. Maybe it's set, I don't know, just by being proportional to that. So actually, Karen, is this what you wanted to know? So this would be fluctuation speed. It was like the square root of the strain rate.
Great.
If you have a reason to suspect that these two dimensionless quantities would be proportionate. All right, so then let's look at the size of the heterogeneities versus inertia number. 1 over the inertia number. It grows, and well, the wiggles are even bigger, okay, around power law. But if you want to fit a power law to that, it's an exponent of about 1/3.
So the delta V was also as a function of I, right? The way you do it.
Yeah. And
so square root of I? Delta V was more or less I or square root of I?
Yeah. Delta V is the square root of I.
Remember what D was again?
I'm sorry. I probably never said it. It's the size of the grains. There have been some simulations recently. Atano has looked at uniform shear, and he found as you shear it, the pressure goes up with the strain rate, and the correlation length for velocity fluctuations also goes up, well, as the strain rate goes down as you get closer to jamming. If you combine those two observations, which he didn't do, you would find actually that the correlation length grows exactly like we see here. The strain rate as the inertia number to the minus 1/3.
Sorry, but n star should go like this correlation length squared.
That depends on your picture of what the heterogeneities look like. Are they compact, or are they string-like?
Yeah.
So we would compare these only if they're string-like.
String-like literally meant that they had width of one particle regardless of the strain rate.
Yeah, their dimensionality would be 1. Yeah. sort of swirls, stringy swirls.
But so what you're doing with looking at image autocorrelations along a given strip, does that mean that you only have access to lengths along the strip?
Yeah, okay, so that's something I worry about a lot, but don't know what to do about my worry. So, right, I mean, here we have inhomogeneous shear. The shear is really changing strongly as a function of depth. And we're interrogating just along, literally, a rod in this really 3D sample where the strain is changing. The strain rate is changing. So I don't know what to do about that worry. Some simulations.
Structure is string-like. Sampling volume is string-like.
Correct. Yeah.
I'm actually impressed by your analysis because the dimensional analysis which leads to the I number, it is based on a homogeneous flow. And in fact, it's really rigorous when you have, yes, when you're either a homogeneous flow, or if you are, for example, on a flow down a plane, in order to arrive at this scaling, you need to make the assumption that you have a local response, in the sense that only the local strain rate matters. And here you are looking deep in the flow. And the very fact that you have actually creep flow at the bottom of your flow is because, in fact, it's not absolutely not local. It's because you have actually energy which is coming from, I mean, you have the flow on the top layer will activate or agitate what's at the bottom layer. So you're really in a situation where you're not, I mean, so for example, the temperature or the velocity fluctuations which are generated by the top flow should matter.
You're saying, like in your kind of analysis, the correlation length in your analysis goes to infinity as the shear rate goes to 0. That's exactly what's happening at the bottom of the sample.
But I think you're saying more about why I controls it, right? Because in these other...
I'm really talking about the granular scaling. I mean, the scaling which leads to the I number, it's derived in homogeneous flow. Yeah. And here you have the reason why you have creep at the bottom is because you have actually propagation, I mean, of vibration inside the depth of the flow. I mean, so it's a very different situation.
I think I appreciate your point, but to me, this I number is really an ansatz. It's really simply doing dimensional analysis. Create for me a dimensionless number based on the strain rate. Really, that's you just start from there and you go with it.
It's very puzzling. It does work.
It seems to work.
It seems to work, which is really.
But there are other dimensionless numbers you can make if you start taking into account the spatial structure. In fact, there's a gradient of the shear and the other dimensionless number you can make out of that.
Yeah, which is what these guys have done, right? For their recent experiments where they put in sort of gradients or non-local things. Yeah. But it works reasonably well.
All right, so let me buzz through Kirsten's experiments now. And so there's Kirsten. This is part of her PhD thesis. And this is work done in collaboration with Emily Vernay, Paul Ratti, and Jerry Golub. And we're working with particles, polymer gel particles provided by Arjun's group at Penn. And the cool thing about these, there's a couple of cool things, is that they're soft, so they can be deformed. And I'll show you, well, maybe I'll skip that part, but I can demonstrate pretty convincingly that when you squash them together, they don't deswell. They deform at constant volume. They're essentially incompressible, but they're soft enough that we can put them above jamming. And the way we do that is in situ with one sample. So we pick a number density that's pretty high, and then we just change the temperature. As the temperature goes up, they shrink. As the temperature goes down, they swell. So we could prepare the sample, lower the temperature, and make a jam. So we do everything with just one sample controlling the temperature. By we, I really mean Kirsten. All right, so as I said, I'll skip all, well, I just have to tell you. We characterize the mechanics of these particles just by putting them in a centrifuge and compressing them. So we measure the packing height as a function of rotation speed and so forth. And from that, you can deduce the modulus of the particles, and by looking at where this asymptotes, you can say something about whether or not they're deswelling or deforming without changing their volume or not. And that's important because even though the size of the change in particle size on a linear scale is modest. The modulus of the particulate material varies by like a factor of 5. So when we look at the rheological properties, we actually take this into careful account. So I skipped that. And we're going to make contact with the rheology using a microfluidic experiment, using an old idea that basically of force balance. So you shove in you arrange a pressure drop across your sample. You look at it from below with a microscope, and basically then by imaging the velocity profile, you get that's backwards. By knowing the pressure drop and invoking force balance, you know the stress is a function of position. The shear stress is 0 at the center of the sample cell. That's why the velocity profile is the velocity reaches the maximum here. There's no strain rate in the center because the stress is 0. As you go farther out, away from the center, the stress increases, so the strain rate increases. That's why you have a parabolic flow or a Newtonian fluid. At the same time, for non-Newtonian fluids, you can measure the strain rate as a function of position. So for the non-Newtonian fluids, say above jamming, it flattens out. You have a sort of a plug-like flow. You can then just measure and compare stress versus strain rate with just one set of movies. So there's some of Kurson's data. And as I said, this is for one sample with different packing fractions, which we arrive at just by changing the temperature. So for above jamming, the stress flattens out to a constant. For below jamming, it seems to decrease continuously towards 0. And you can fit that pretty well to a Herschel-Bulkley form, that's the dashed lines, and use that to try to collapse the data.
Excuse me, is it really, okay, to say, how are you sure that it's really constant, not just going down much later? I know it's an
What can I do?
question.
Yeah.
Yes, I know. But so I'm asking not the data, but you.
In principle,
Data don't tell you. I mean,
in principle, why couldn't it go down? I don't know. I can't rule that out. Right? Maybe at extremely slow strain rates, thermal effects would be important. I tend to think of this as being an athermal system. Maybe that would be important. I don't know.
But I'm sorry, you said that the modulus of the particles changes when you change the size. Are you scaling the stress by that factor, or?
Well, not yet. Yet. So here, stress divided by that factor, and strain rate times the viscosity of the base fluid, which is just water. So that's the viscosity of water times strain rate, and scale them with the particulate modulus, and then powers of distance to jamming phi minus phi c. This is the sort of scaling that Olson and Teitel did in their PRL, and we can use that to collapse the data pretty well. And we can think there's some sense you can make out of these exponents, but that's not supposed to be the point of this talk. I think the point here is that we can measure the rheology, and the rheology is pretty well controlled. And at the same time, heterogeneities grow. Here, we're going to do the same trick as was done in Hiroki's experiment. We'll just look at correlations along strips. So near the edge, the strain rate's high. So the decay of the order parameter is fast, and the peak height is not very high. As you go closer to the center, the strain rate decreases. So the time scale goes out, and the peak heights go up. So the heterogeneities are growing as you go to lower strain rates by going towards the center of the sample. So we've got all that data, and here's almost all of it organized. Each color represents a given packing fraction, and it's plotted versus strain rate. And what you see is it's a log-log plot with lines of the data that have a slope of minus almost a third. The solid points here and here are the ones below jamming. So this is far below jamming. As we go towards jamming, it goes up to these other solid points. Right around the phi c, it's up here. As we go further and further above phi c, we go back down. So in terms of packing fraction, far below phi c, going up towards phi c, going above phi c, we go back down. So there's some scaling, not just with strain rate, but also with packing fraction, which we can uncover by just plotting the coefficients of these versus packing fraction. And here's what comes out of the wash, is that this collapses the data quite nicely. The size of the heterogeneities goes like strain rate to about minus 1/3, phi minus phi c to the minus 4/3. So you've got two ways to approach jamming in this experiment, by strain rate or by packing fraction. On either way, no matter which one you choose or which combination you choose, the heterogeneities grow as you get closer to jamming. So that's the same exponent that we saw before with the granular systems and with the simulation work. This is an exponent that I haven't seen before, but I wouldn't say I understand this one for sure. So to me, that's an interesting question. And time scale goes too. But let me stop there and just say again, the theme is heterogeneities as well as other sorts of unsteadiness grow as you approach jamming. Pick your favorite way to approach jamming, and we tend to see that something unsteady develops as we go towards jamming. In particular, the size of the heterogeneities grows as we approach on jamming. And we've seen that for 3 different systems and 3 different sets of ways of going there. And a couple side themes I think are important is the idea of effective temperatures and connecting up to the macroscopic rheology. I want to thank Adam, Hiraki, and Kirsten. They're the ones that are on the ground doing all the hard actual work. And Emily, Paulo, and Jerry collaborated with Kirsten on those works. I also want to thank a bunch of folks for discussions, as well as Arjun and his group for providing samples. I want to thank you for your attention.
Say like power spectra of the fluctuations in velocity. Like, I mean, you calculated this delta V, right?
Yes.
Which is just the width of the distribution, right, of those fluctuations. If you take a time trace of the velocity, could you do power spectra and look at the scaling of it?
We actually have that data.
Great.
Usually it's hard to come by because usually when you do these measurements, you assume that you're doing an ensemble average and then do a time average to accumulate statistics. But we have a way of time resolving this. So we have that data. We haven't looked at the power spectrum.
It'd be great.
Okay, thanks. You'll tell me why.
Yeah. But we have sort of a simple theoretical picture of what you might find. You find scaling for the high, and so we have some sort of set of exponents. It'd be nice to compare.
Okay, good. Yeah. Okay.
Theory motives are easy to find.
For this experimental setup, can you also look at molecular systems beyond spheres? I know it's.
Do you mean?
For example, let's say you just mean objects that are on ramp.
No, that have shape.
Yeah.
Because I think nobody has really looked at this. But I mean, we think
the only
microscopic thing.
The only thing we've done along those lines is to look at rod-like particles. Sometimes they're polar, sometimes they're not polar. That's the only thing we've looked at. Nothing more complicated.
But someone gets the same phenomenology?
You asked. No. Absolutely not. Let's see.
There they are, see? Clearly not true.
I don't know which one I don't know what I'm getting there.
300 megabytes.
There you go.
So those are fluidized rods.
These are vibrated then?
No, they look like they're vibrated, but that's because there are waves passing through here. These are fluidized.
Same kind of thing that Adam does?
Same kind of thing. Let me find a different one, maybe.
What are they made of?
These are pieces of plastic, just plastic dowels. This shows the waves a little bit better.
Can you make them shorter? And because this is a little bit,
okay.
It's basically a plastic.
Here, I made them shorter.
How's that for surface?
So, but in terms of making things, I don't know, like lock and key, or I don't know, funny. We haven't played around.
No, I mean, because there are theoretical predictions on what happens to the orientation and the translation dynamics as a function of the lengths. And so it's a very nice system to test.
Why did these form strings?
That's John.
The piles of them stacking, and they just go marching along.
That's John.
As a matter of fact, yeah, John, you should.
What were you
I hate
asking?
it when people say that. I'm actually not sure I know what you mean. You mean?
I mean, look, you see
you mean this is a string?
No, they have stacks, and then the stacks sort of go wobbling through there like maybe like polymers pretending that they're snakes.
You got me.
Snakes pretending that. I don't think that have to in order to fill the volume, fill the area.
But they don't. You know.
I mean, the thing I wonder about this is, I mean, this is an illustration of what I was saying earlier about constellations. If you look at this picture, it doesn't look particularly like there's any long-range orientation order, but I'm actually not sure. Doug actually has a student looking at that right now. If you look at the previous picture, it looks a lot more like it's orientationally ordered, at least to me.
You mean for the longer rods?
Yeah. Yeah.
But for the shorter rods, didn't like old simulations by Frankel show these kinds of these domains? He called them something. You get, and Seth saw those when he looked at short granular rods. And if you make them short enough, you get not that kind of orientational order, but these domaining things.
But if you make them short enough, you get domains that aren't much bigger than a single rod.
Right. But this was sort of intermediate, right?
This picture looks as if you're looking at it right side up rather than on its axis, on its edge. And this would be, most of the rods are up down.
I mean, yeah, there are quantitative ways to decide that.
Yeah.
So this is from the thesis work of Lynn Daniels. And,
so do you see the same?
Fortunately, he's got his degree.
Do you see the giant density fluctuations?
Yeah, they're density. Yeah, they're large density fluctuations here. It's bigger than the square root of n.
How tall? How wide, I guess, is the diameter?
The aspect ratio is like 11.
I noticed there's one that's fallen on top of the other guys. I'm wondering how often that happens. It's sort of the bottom right-ish. Not quite
Right
the
here.
bottom on the right.
Yeah, that's a danger when you have very long aspect ratios.
Actually, I should add, in the interest of truth in advertising, that Doug's also looked at the fluctuation spectrum of these, and it's not what's predicted by the Ramaswamy Simha and Toda model. I have some half-baked ideas about why that might be so, and I'm in the process of trying to completely bake them.
What happened in Menon's experiments? Did they look at the fluctuation spectrum?
No, they didn't. They looked at the number of fluctuations and worked the way we said they should, and stopped there. They decided to leave well enough alone when things were working. But it's, I mean, you know, Doug, as you can see, you can do anything with this, which means there's a lot of opportunities to disprove things. And the spectrum at least shows that the simple interpretation in terms of just a standard model for active mathematics doesn't work for these things. But
what happens? I thought you should talk to you later.
Yeah, I can tell you what happens. I mean, Doug can tell you what happens. I can tell you what the theory says.
Yeah.
They're not the same. They basically, you find a finite speed for the hydrogen theory. Maybe there's like q squared speed, and it just goes to 0 speed.
So the 1 over q squared gets cut off? The q squared gets cut off?
That's what always intrigued me, is when the theories are wrong.
I think John's taking it.
Okay, thank you.